Okay, so previously what I showed you that at least in some cases, all these three ideas, yes, if we use this arbitrary lift where we allow arbitrary permutations, of course, yes, we are not limited. So the only thing we need to take into account that every A should commute with every B. And if you look at our paper on lifted product code, we can see that our general definition was like that. Yes, we define it like hypergraph product codes. We substitute each element with some square matrix. And if these square matrices commute with each other, then we get what we call lifted product code. And in terms of graphs, it can be represented like that. So it corresponds to this idea. And here, another two ideas, and both these ideas are more general, yes? So here we can have graph bundles that are not coverings of product of two graphs, yes? You can easily find such graph bundles. And for balanced product, you even can get some very weird graphs that do not have the same local structure, for example, like this, yes, like product structure. And so both these ideas are much more general. Okay, but what we are going to discuss next. So the key idea is here to show that in order to construct codes that have constant rates. So before we already saw that we have this lifted product construction that give you codes of linear dimension, yes, because we just instantiated hypergraph product codes with group algebra elements, and we automatically have the number of qubits and the number of checks scales linearly, yes, with the lift size, and it automatically just have constant rate. So it's not, rate is not a problem here. The problem is the distance, and for the distance, as we saw previously, trivial ideas like just take two codes that has some good properties, they fail, they completely fail. But in order to describe how, but if you read our paper, you saw that we also mentioned, in fact, it was not our main purpose, we also mentioned classical locally testable codes. And it turned out that all this were very well connected. And let me explain why. So I hope that everyone here in this room already knows the definition of locally testable codes. I just show you for clarity and just to fix our notation. Yes, so we call LDPC codes locally testable if it has this property, which means that the weight of the syndrome grows linearly with the distance of the test vector to the code. Yes, I hope everyone in this room already knows this idea, and you already saw many examples in this workshop, yes, of locally testable codes, and one of these very famous examples are a Hadamard code, and I hope that everybody knows it. Yes, it's just a set of linear functions that can, and we can, of course, very easily check whether the function is linear just by looking at this equation. And it involves just three entries. Yes, it's local code. We have local check, and what we can see that we have too many checks here, yes? So how many checks we have? So the length of the code is 2 to the n, but the number of checks is equal to 2 to the n by 2 to the n. So we have checks much more than needed, which means that this code has a lot of redundancy, and which means that we also can take into account this redundancy and consider some other code that checks on checks, yes? And this way we get this chain complex. And in fact, okay, but let us switch to some very simple examples. So the natural question to ask whether, for example, some very simple codes like repetition codes are locally testable. And who knows the answer? Is it locally testable or not? Of course, yes. But if you try to think about it in a very straightforward way, yeah, you can just start with a standard parity check matrix, and you can see that, in fact, this parity check matrix does not satisfy our definition, yes? In order to see this, let us consider this code in this graphical way. So we assign our bits to vertices. Yeah, it's a little bit unusual. So this is what I call transposed Tanner code. Yes, and I talked a lot yesterday and confused a lot of people by this. Okay, and this was on purpose, of course, because I think this idea should be studied more. And here, so I put bits on vertices, and each bit send it to the edges. So it's kind of Tanner code where we have repetition codes in each vertex. And if all the edges agree, for example, this one and here one, so they agree. And if they all agree, then we have a code word. And you can see that, in fact, this construction describes repetition code. But let us, and it exactly corresponds to this parity check matrix. You can easily see this. But let us see why this parity check matrix doesn't satisfy the definition of LTC. This is very simple, because if we can show an example of a code word where we have half ones, yes, and we have only two syndromes which are on edges that are unsatisfied. So we do not have agreement here, which suggests that this code is not locally testable. Okay, but we can fix this. Yes, what if we just and of course this parity check matrix just corresponds to co-boundary operator for this is what is called co-boundary operator for this graph. And each vertex, yes, it goes to the sum of two edges. And the natural question we can ask then whether we can fix this with graphs which are sparse. And in fact, we can do this just by using expander graphs. And you know that expander graphs has this property that in fact, this was one of the earliest definitions of expander graphs, that we cannot divide, if we divide it in two parts, then we have many edges between them. Yes, this is just was an original, almost original definition of expander graphs. And we can see that it exactly corresponds to our problem. Yes, we can use this expander graph, and these expander graphs give us new parity check matrix. Yes, it's co-boundary operator that has this property, that has this local testability property, which suggests that maybe there is some connection between expansion and locally testability. And in fact, of course, you know the answer that there is such a connection. Okay, so here the same idea in a little bit more detail. Yes, so we introduce what is called co-boundary expansion of graph, or in particular, this case, it is also called the Chigger constant. So it's so we divide in all possible ways, yes, in two parts, and we look at the number of edges that crosses these two parts, and we just take the minimum. So it's the minimum possible value here, and it is called Chigger constant. And I also want to mention that here we have this, so we also have some additional trick here, I should mention, yes? So before I only described this parity check matrix, but in fact for our repetition code, we also have generator matrix, yes? That contains just one row. And this, so we also add this generator matrix. And in topological, topological terms, this corresponds to the, we consider this graph as a simplicial complex. And as Max already showed, yes, when we consider simplicial complexes, we also have this face that doesn't have any elements, yes? And this space, it corresponds exactly to this face. And if we interpret it in this way, yes, then this Chigger constant can be defined as this parameter that corresponds to local testability of this repetition code. So this is just an equivalent definition. And we can also consider a small set version of this. Yes, if we can just restrict ourselves only to small subsets, then we get a small set version of this Chigger constant. Yes, this is exactly the same, but we restrict ourselves to small sets. Yeah? Yeah. It's minimum of two sizes of the vertices. Numerator. Here. Yeah. Thank you. That's true. The delta 1, yes. Thank you. Okay, and why I showed it to you, because you can naturally extend it to simplicial complexes that were already described by Max in his previous lectures. Yes, so here's the picture similar. So we have these different layers. I have a little bit different notation for dimension. So we have 0 dimension for vertices and -1 dimension for this empty set, but it's not that important. Okay, and we have a chain complex, yeah, that has each layer that corresponds to the layer of this simplicial complex. Yes, and on each layer we can define these homology groups, and we can also define these Chigger constants. And this is what is called boundary expansion in dimension I. Yes, it's when we consider the corresponding layer, and we can also define the small set version. Yes, and it's kind of similar, it's almost equivalent to what is also called consystolic expansion. It's not exactly equivalent, but it has very, very similar properties. And there was a very nice observation in very long before ago by Tali Kaufman and her numerous collaborators, that all this is kind of related both to locally testable codes, and they had 2 papers in 2014, where in one of the papers they showed that large expansion is kind of related to this soundness parameter of local testable codes. Yes, and another paper they also very, very briefly mentioned that there is also some connection with the quantum codes. Yes, and in fact, those papers contain some other interesting ideas that we used in our construction of good QLDPC codes. And in particular, this approach, yes, was also used in construction of one of the early examples of the codes that break this square root barrier, but just by a little bit. But they still use this technique that, in fact, was used in the final paper. So this paper was also quite crucial to construct good QLDPC codes. And so I also want to mention that there is a generalization of both, yes? So you can consider also what is called quantum locally testable codes. What is this? So here we consider a graph that consists of 5 parts. So we have chain complex, yes, that of length 4. And in the middle we have qubits, we have X checks and Z checks. And the definition of the quantum locally testable code is very simple. So it's just a good code, good LDPC code that has linear distance and linear dimension, but it also has the property that this codes defined by matrix HX and HZ, they are LTC. They have this LTC property. And why these codes are interesting? Because many people connect them with PCPs, and by the way, they already found some applications in fault-tolerant quantum computation. So this recent result that showed that almost good QLTC exists, it was already used to provide some interesting new fault-tolerant schemes that has very good parameters. So it already found some applications, though we currently do not know whether good QLDPC quantum locally testable codes exist. So it's still an open problem. But even the ones that we have right now already found some interesting applications. But here, before I want to describe you some also very interesting idea, the idea of Schiff codes that I call Schiff codes, which is relevant and it is required to understand all the definitions that will follow. So this idea is also quite old. So originally there was a nice paper by Dinur and Kaufman that described Schiffs and connected them with property testing with agreement testability. And there were also some other paper by Mishulam that connected Schiffs with Tanner codes. And the idea is as follows. So if we have some, for example, simplicial complex or some more general complex, so we can consider is a poset. Yes, every complex, so it has cells of different dimensions, and they contain some other cells, so we have a natural poset. And in this poset, we have some maximal elements, and so this is the elements of the largest dimension, yes? And so let us denote by this set of maximal elements, and this is a link, what is usually called the link. And what is interesting, so every poset is also a topological space. Not so many people know about it, yes, but every poset can be considered as a topological space. But since it's a topological space, you can define homologies, you can define everything, yes, you can define all the stuff that are studied in algebraic topology and apply it to posets. And in particular, you can define a sheaf. A sheaf is a notion from algebraic topology that can be defined on arbitrary topological space. And in fact, it can be also defined on poset. And what I mean, so this is all, if you look at Wikipedia, you can find some very complex definitions. So let me just simplify this. What do I mean by sheaf code? So a sheaf code is just a Tanner code, just a special case of the Tanner code. So in fact, it's just a linear code with some fixed collection of local codes. And these local codes are indexed by the elements of this poset. So in a sense, it's a Tanner code with some hierarchy of local codes. Yes? So it's very simple and, of course, well-known definition. And so here I showed it in the picture. Yes, we have our bits, and we have a hierarchy of different local codes. So we have the trivial codes that just involves one bits. This corresponds to codimension 0. I call it codimension 0. Then we have maybe some larger, yes, local codes, and etc. And we have this property that, which is important here, that if we restrict every code word from the large local code to subset that corresponds to the local code word, then we get a code word from this local code word. So this is important. So we have, yes, we have larger locality, and we restrict it to some subset that corresponds to local code, and we should get a code word of the local code word. And this idea, I don't have time to describe to you, but this idea is exactly what is a sheaf, what a sheaf on topological space looks like. Yes, in topological space here is just our poset, and open sets are just, yes? Yeah. Yeah, we can consider Tanner, standard Tanner codes with just where hierarchy is very simple. So we have first layer that, so we always in shift code, we also have this layer that corresponds to bits. That's not interesting, yes? But we also have many other layers. In Tanner codes, we just have one additional layer, and that's all. But here we have hierarchy of localities, yes? So, and there are many cases where you need this, yes? For example, take tensor product code, yes? Tensor product code. We have what are localities we have? We have individual bits. We have local codes that corresponds to rows and columns. And we also may even give another local code, that the global code, yes? But in high dimension, the situation is even more interesting, yes? So when we have a multi-dimensional version of tensor product codes, we have many, many different levels of locality. And in order to describe it, it is interesting to consider it like a code defined on some simplicial complex. And it turns out that tensor product codes are sheaf codes defined on complete and partite simplicial complexes. So Marx also described this in his previous slides. Yes, he described simplicial complexes that has several parts. We choose some vertices here, and here are our simplices, and it can be shown that high dimensional, so for example, in 2 dimensions, we have just complete graph, yes? Complete bipartite graph. And from the work of Tanner, we already know that indeed we can consider tensor product code as a Tanner code defined on complete bipartite graph, yes? So this is all is very old and well known, but in high dimensional case, the natural object is to consider complete and parted simplicial complex. Okay? For Reed-Muller codes, I'm not sure I know the good, maybe, so we need, yes, to consider all planes, all possible planes, yes. Okay. Yeah. Yeah, and this, yes, in this case, yes. So it means that if you have a code, you can also consider you can fix some hierarchy of localities. And in fact, you can do it in several different ways. Yes, there is no one special way, but usually for some natural code, there is some natural object where you can define it. For example, yes, for tensor product codes, this is exactly this and partite simplicial complex. And okay. And here, so now I want to describe this high-dimensional version of simplicial, high-dimensional version of this Sipser-Spielmann codes. So first, let me first briefly describe what is usually called Zemmer codes. It is not a very well-known concept, so it's so I initially learned about this in the lectures by Spielmann, but it's not a very common name, I would say. So it's a slight variation of original Sipser-Spielmann construction, where instead of Kelly complex, we consider it's what is called its double cover. So so we have a group G. So we have 2 parts. We have a bipartite graph, and we have vertices. Here we have vertex G, and here we connect it. So we have group G, and we have a symmetric set of generators, yes, as usual for Kelly graph. So we can see the standard Kelly graph, but here we connect G with GA, where maybe not A, S, where S is one of the generators. And we get what is usually called double cover of Kelly complex. And why I got interested in 2020 when I first encountered this paper, because these codes are exactly what we need to use in lifted product construction, because they have parity check metrics that can be described as a matrix of a ring, yes, because we have a free action of the group on here and here. So this is because this graph can be described as a lift of this very simple bipartite graph with two vertices. Yes, so you just put these generators. Sorry, small. R. Okay, R is so H is a matrix R by delta. H is a matrix of the small local code. And you can check that we can describe it. So we have these bits, and so we have these checks that check this, for example, this part, and we have these checks that corresponds to this part of the double cover. So it's not very hard exercise to check that this is indeed a parity check matrix, yes, of this code. And the length of this code is also very simple. Yes, it's just the number of edges. So the length of the code, number of edges, multiply by the lift size, by the size of the group. Okay, is it clear? Okay, great. And local codes, if local codes satisfy this condition, this goes to Sipser-Spielmann original idea, then we can use using exactly the same proof techniques and show that these codes are good. Yes, and why they are usually referred to as Zemer codes, because we can run Zemer decoder, famous Zemer decoder that runs faster than the decoder that proposed one in the paper by Sipser and Spielmann. Okay, and we can also view it like a shift code. Yes, we have several levels. We have individual bits. We have local checks. Yeah, and we also have like a global code that corresponds to this. So this is a standard Tanner construction. Yes, every Tanner construction is a shift code. And now we have this idea that corresponds, is almost exactly the same as Dinur's famous code on left-right complex. So here we just consider this left-right graph. We add, of course, here I only showed you one skeleton of this complex. Yes, we also need to add squares. So for every pair of edges, yes, we also have a square. And we can also define this code. And it turns out that this code is just, if we apply it's not lifted product, so it's what I described before. Yes, it's a code where A and B are Zemer codes. If A and B are Zemer codes, if they are defined by these parity check matrices, yes, then this code that I showed you before the break, it is exactly this, yes, and so they're just equivalent to each other. It's a little bit different from what was in Dinur's paper because they do not have these 4 parts, but almost the same idea. And what they showed in their paper, so I just, so it can be also applied to this case, of course, that if here we have a tricky part. So here I mentioned some new property that I didn't describe. Yes, it's kind of high-dimensional analog of the distance. So here we can see that this code involves several levels of hierarchy of localities. Yes, we have 3 levels: bits, rows, columns. This is the next level, and we also have square here. This square, yes, so that corresponds to tensor product code. So here we have 3 levels of locality. And this is exactly why we get a chain complex out of this that has 3 levels. Yes, because we have 3 levels of locality. And it turns out, so this, in order to ensure that this construction works, we need some special property for the pair of codes. As it turned out that this property was closely related to robustly testable codes and also to agreement testability of tensor product of codes. But I will describe this property in a minute, but I should say that in high dimensions, it is no longer corresponds neither to agreement testability nor to robustly testable code. So it's a different property. But in 2 dimensions, it is exactly, so you can choose one of these and they are all equivalent if the local codes has good distances. In this case, they are all equivalent. But I will describe it. So we call it product expansion, and we were inspired by these early papers by Tali Kaufman and co-authors that showed a very general idea. What followed from their papers, that when you construct high-dimensional expanders, you need to ensure that all the links has expansion. Yes, and you during this conference you saw many examples of this. And when we looked at these codes, we noticed that so we need to ensure this local expansion in each vertex of our of this complex that corresponds to left-right Kelly complex. And in order to ensure it, so we need to have this co-boundary expansion that I described it to you, but we had to generalize it a little bit. And it turns out that this is exactly the co-boundary expansion that I showed you previously, but applied to situation when you have a simplicial complex, but you have some codes defined on this simplicial complex. So it's a very simple and natural generalization. In fact, you can read in more detail and the general theory of how this works in a series of papers, very comprehensive papers by First and Kaufman. And so we just applied it to tensor product codes, and they applied it everywhere and showed some many different examples, new examples, also interesting ideas, how we can use it to construct some LTCs and quantum codes. And here is a definition. So we need to, first of all, we need to define a chain complex out of the tensor product code. And we already saw that we have this, yes? When we describe hypergraph product codes, we already saw that we have a natural chain complex that corresponds to the tensor product. And but here I use a little bit different. So here I use these matrices, so I interpret them as generator matrices. I will describe why it is so. So here we have the following complex, yes, and the definition is as follows. So we consider this complex, and we introduce a new norm. So when you define co-boundary expansion, you can use some norm, yes, on chains. But here, so our norm involves what we call block Hamming norm. So we just count the number of non-zero blocks, and to this complex we introduce this particular norm. So here we have our chunks, our blocks, where we have rows, here we have columns, and here we have the finer one, yes, where we have just bits, yes, and here we count the number of bits, here we count the number of columns, and here we count the number of rows, but here we count just whether it's 0 or not. So it's a very, very natural situation. In fact, you can easily understand why we need this. So, so maybe, so let me just explain this a little bit more. But okay, let me skip. I don't think we have enough time. Why we choose this? But there was a reason for this, very natural reason. And you can just define, so here I showed you two-dimensional case, but you can also consider this chain complex in many dimensions. Yes, we have tensor product of chain complexes that can give you chain complexes of that has more terms than 3, yes, and you can define this Chigger constant. And the idea is to define it on the last layer, on the last meaningful layer. Yes, so, okay, yeah, the questions?
Some of the weights of all the local codes?
Maybe I need just to describe this norm. So what was our intuition? So the intuition was as follows. So we have some tensor product code, yes? You can have you can consider some, so here we have some numbers, yes? In this, maybe, I don't know, zeros, ones. And we have, so we have a copy operators like that copy, so we have restrictions. So we have a sheaf, yes, and we have restrictions. So here we restrict to columns. Here we restrict maybe to rows. And then here we have restriction. So each row is restricted to individual elements. And here we have a finer restrictions like this. And we get exactly the same. It's a little bit tricky. So this is exactly the same data, yes? So here we have a matrix, and we have a linear map, restriction map, that when we restrict this matrix to its row. And here we have also a matrix, and we have a restriction map when we restrict to column. Yes, and then we also, so here we can describe these linear maps as a restrictions. So we do not even need parity check matrices, which is very cool. Yes, so usually when we define these complexes, you saw that we always use some parity check matrices. In fact, I can say that in this case, in this boundary expansion, it does not really depend on parity check matrices. So it's a property of the code, which is very important to understand. And so we can also reconstruct this complex. So here I showed you that we have the space K1 by K2, yes? But every such matrix gives you a code word of a tensor product code, and this is this one. After that, we restrict it here, yes? And we obtain some element from here, for example, yes? So these are just restrictions. So in this description, this complex, I do not use any parity check matrices. Of course, we have this parity check matrix when we choose the generator matrix for this tensor product codes. It is hidden in some way, yes, but it shows you that this, in fact, but in terms of this norm that I used, yes, we do not, it really doesn't matter what parity check matrix we use, so it's independent of this. Okay, and so here you can define these Chigger constants on all layers, but it turns out that the most important layer is the last one, last meaningful one, like shown here. So in the case of tensor product of two codes, we have not so many layers, and this is exactly the reason why in two-dimensional case, all these ideas like robust testability, agreement testability, they all match to each other because we have not too many layers. But when we have many layers, it turns out that there is a counter example that shows that you can have codes that have robust testability property, that have agreement testability property, but they do not have good co-boundary expansion on the last layer. So it's a stronger property. And in fact, all current constructions for dimension more than 2 involves this property. So we indeed, it seems like that this is the correct way, yes, to generalize it to higher dimension. And as I said, so we call it product expansion because it's co-boundary expansion of tensor product codes. Okay, but let me even further describe it, this idea, because I think that not many people understand it correctly. What if I consider tensor product of two repetition codes? Just our simple example. What we get? So we have the following situation. And how we define it in this case? So here we put some bits. And these bits are propagated to edges. So we put some bits here, put some bits here. And if we have agreement, yes, so if you look at this, the first part, yes, then this corresponds to the number of edges that agree with each other. Yeah? So it doesn't agree with each other. So the number of edges that doesn't agree with each other. And for repetition codes, it means that this is exactly the Chigger constant of this bipartite graph. So in the special case of repetition codes, this idea corresponds exactly to the Chigger constant. So you can think about it as a generalization of this. If we just put not repetition codes, yes, but we put code words from some local code here, and they give you some bits here and here. So we choose some code words, C1, C2, and etc. And then we check the disagreement. And as you can see, yes, why it is related with agreement testing and agreement testability, because you also do this with agreement testability. But in high dimension, unfortunately, it looks like that this is a different concept. So it's no longer, it's stronger than agreement testability. So it's not enough to just to have agreement testability. At least we don't know currently any construction that from just agreement testability gives you codes of dimension higher than 2. So, but in 2 dimension, agreement testability is more than enough. Okay, and I think, so here is this, my example that I showed. Yes, so we put code words from C1 here and C2, and this is exactly like a Chigger constant. And now let me just briefly describe how much time do I have? 50? 50? 15 minutes, okay, that's cool. So I also want to mention this, I already mentioned QLTCs, yes, and there was an idea that you can generalize all these local testable codes and quantum LDPC codes to higher than 3 dimensions, and in order to use this construction higher than 2 dimensions, so the idea is that you consider some natural generalizations of these left-right complexes or some other complexes, yes, in higher dimensions, but the local codes condition is almost exactly the same, but here we use these high dimensional versions of these ideas, yes, that I already mentioned that they are different, yes, they are different. And it turns out that if we have good local properties of these tensor product codes, then we can get very similar constructions that give you almost good QLTC codes. But by almost good, I mean these codes has distances that grows like n divided by log n, up to log n factors. And also the soundness parameters are also not perfect, but almost good. And what's interesting that if we have some natural analog of this left-right complex in any dimension, yes, then, and if we can use arbitrary codes here, yes, then we already have good QLTC codes, because all these proofs, they works also in this case. And the main limitation right now is that, so we have some high dimensional analogs of these left-right complexes. Those are called Ramanujan-Kelly complexes. They already exist. They were shown to be exist long before. But the problem that they have that you cannot use just arbitrary codes with them. The codes that you can use with them, they should have some additional property. For example, you can always use repetition codes. Yeah, any chain complex, for any chain complex, you can use as local codes, just repetition codes. It works with any chain complex. But repetition codes has all possible symmetries, yes? And in fact, it can be shown that if the codes has some symmetries that are related to these cubical complexes, then you can also use these codes with Ramanujan cubical complexes that, as you know, recently was used to prove some breakthrough results, yes? And we can use exactly the same Ramanujan cubical complexes, also try to construct QLTC codes. But the main problem, open problem, is how to find the codes, the local codes, that has this symmetries. Yes, so they need to have some symmetries, but they also simultaneously have these properties. And this is an open problem. Right now, what we know that if we choose sufficiently large finite field, then with high probability, we have both these properties. But this is not enough to use it with codes with some specified symmetries. Yes, so this is an open problem you can try to solve, because if you solve it, then you solve the good QLTC problem. Okay, and sorry?
How large is Q?
It's so the logarithm. So it's quite large field, but so it should be large enough. At least at least, as far as I remember, at least just length of the code, maybe multiplied by some constant. So it's not. So it's higher than for Solomon codes. For Solomon codes, we need just length of the code. So this is a little bit high, but not that high. So it's. But this is not a problem. So you can use arbitrarily large Q because it will be constant. So it's here we are talking about local codes, and they always have constant size. So so it's not a problem at all, this field size. Okay. Let me also, maybe if I have time, describe one of the key ideas in the proof, in all these proofs that involves large minimum distance of QLDPC codes and good soundness parameters of locally testable codes. So these ideas are quite simple. Maybe I can describe it in a very easy and fast way. So what I also forgot to say a little bit. That this idea, yes, that corresponds to this classical codes, it can be also, since it involves three parts, yes, we can also reinterpret these parts as X checks and Z checks. And we can also construct not only locally testable codes, but also good QLDPC codes. But the idea is exactly the same. And the code that in particular we use in our paper is the following code. It's just a lifted product codes applied to two Zemmer codes defined on the same graph with the same generators. In our construction, we do not need different generators. And here we have transposed. And this is, so this transpose size is used to make sure that we have linear dimension in the same way. So the proof is exactly the same as for hypergraph product codes. Yes, when we combine two matrices, some particular sizes like H with H transpose. So these matrices, they have the same parameters, but they are different matrices. But their shapes are the same. And here we have the same proof that works with hypergraph product codes, also with lifted product codes. But here we also need some conditions on these local codes. And these conditions are similar to this, but we require that this and this both this should be large, like so these analogs of minimum distance, they should be also be large. But here we consider, yes, we consider not just these codes, but their duals. So this is interesting. So all this construction, and in fact, you can you can reinterpret this object differently. Yes, you can assign X checks and Z checks here and here qubits, and you can assign I don't know, you can assign qubits to the squares Yes, you can. So you can interpret this object in many different ways. And what is changed after that? So you change these conditions. So you either put some do or just remove some do. But all these conditions are kind of the same. Yes, and which means that all these currently known constructions of good codes, QLDPC codes, they are very well related. But unfortunately, I haven't seen any paper that shows this very formal relation between them. People just show in pictures that they are kind of related, but they didn't show how, in particular, they are related, formally related. But they are definitely related, and it's also an interesting problem just to show the formal correspondence between and how. And so my conjecture is that so we can have some more general argument that can work for all of these constructions simultaneously, because you can see that they involve almost exactly the same things. So we work on the same complex, but interpret it in many different ways. Okay, but let me tell something about the proof. If I have, how long? The end. Okay, maybe that's enough. Maybe that's enough. So one of the technical and simple parts of our proof, the proof of Dinur is a little bit different. So in our case, so we rely on early ideas of Tali Kaufman and her co-authors related with local minimality. So in Dinur's proof, they use mostly this agreement, testability, and some random walks. So in our case, we have the following situation. So we have let us describe this way. Okay, let us have some complex, maybe possibly of many dimensions. And so what we define the property which we borrowed from from the papers by Tali. So she mentioned something similar in many different papers. And so it wasn't formally defined in none of her papers, but the idea was can be found easily in many of her papers. And so we call it locally minimum distance. So this is a property that is defined in the following way. So it's, let us consider some chain complex. For example, chain complex defined on simplicial complex for simplicity, on a square complex, yes? And here we define the smallest weight of non-zero cycle. So we look at the code word of non-zero code word that satisfies this parity check matrix, which is what is called locally minimum. And the notion of local minimality is crucial to this co-boundary high-dimensional expansion, and it's defined in the following way. So if we have some code word of a quantum code, you can always reduce it by adding some boundaries, yes? And for example, you try to apply, so let me show it in the graph. For example, we have this Tanner graph. Here we have qubits. I will try to describe it in the most simple way so you can understand. So here we have our code word that satisfy all these checks, yes? And now what we can do, we can try to add this element that corresponds to the element of some simple boundaries that corresponds to one vertex. So for example, in simplicial complex, so it means that we can remove, for example, in the case of toric code, we can try to remove, to add some square, yes? Some elementary object. And if we can try to do it, and this way, so we can try to reduce the weight of this code word. And the code word is called locally minimum if we cannot reduce its weight locally. Yeah, we can still maybe decrease it globally by using linear combination of this, yes, but we cannot decrease it locally. And in this case, it is called locally minimum. And we define the property that is called locally minimum distance. And we can also define it using different norms on these bits. And what we found that we need to consider this, if you see, so we have naturally decompose each bits on some groups of bits. Yes, that corresponds to the locality. And it turns out that it is much, much convenient to introduce here not just the standard norm, but the norm that counts the number of non-zero blocks, like we did in our definition of co-boundary expansion of product code. Yes, we defined this norm that counted the number of blocks. And here we use the same norm. Yeah. Mm-hmm. No. It's so yeah, of course, in the core set we have some global minimum, but this one could be different because it's so here we can just consider locally minimum code words, not all code words. Yes, globally minimum is also locally minimum. Okay, so so you mean that if we consider globally minimum, yes, we have globally minimum, but we yes, we cannot remove it. Let me. Yeah, I already have this question before, so I was thinking about it, but there is some problem here. So we, let me recall what, there is a problem with this approach. So you cannot just define this property as you said, like a global, because, first of all, maybe this would be, so it's not non-zero. What, for example, if you have some code words which is degenerate, so which is, but you cannot decrease its weight locally. Yeah, which is degenerate, but you cannot decrease it locally. It can be lower. So it's in the boundary. But you cannot prove that, but you cannot go to the zero because you cannot, so you stuck, yes? So you started with something that is in the boundary, and you can go to the boundary, yes? But you cannot do it locally. Yeah, but this is a very good observation, yes. And we were already asked about this many times. Yes, I just forgot. And what works here, that it turns out that this value is crucial to prove all the good properties. So first of all, you already see that this, if this value is high, yes, in this level, then it means that the minimum distance of the quantum code in this direction is also high. And we already mentioned this, yes, because if we have some non-trivial local code word, yes, so we have some, we try to reduce it, yes, but so this value, so the minimum distance of the LDPC code should be at least as high as this value. Is it clear? Okay, just look at some non-trivial code word, yes? And we can try to add boundaries to it, and then then we will go to some locally minimum code word that cannot be reduced further. And its weight is higher than this, because this is the smallest locally minimum code word. Yeah? So it means that if we have, any non-trivial non-trivial code word of these QLDPC codes, yes, it can be reduced somewhat using this local, by removing these boundaries, yes, but it cannot be smaller. So its original weight cannot be smaller than this one. So which means that if this value is high, then the minimum distance of the QLDPC codes is high. But this property is also related with local testability, which is also quite surprising. And this was also noticed in the early papers by Tali Kaufman and co-authors, and was used directly and indirectly many times. And the idea is as follows, and the idea is exactly the same. Here we consider this code defined by this parity check matrix. And now this is a syndromes, yes? This is a syndrome, so we have a different interpretation right now. And since it's a syndromes, what we need for local testability? We need a way, so if we have small syndrome, then we should find some vector that, if we have some small syndromes, that this should imply that this vector, so its distance is close, yes, to 0. And if we find some vector with sufficiently small syndrome, let's apply this boundary operator to it. We get some syndrome, and then this vector will be the element of this cycle code, yes, that satisfies this parity check matrix. And we can apply this, if this quantity is high, yes, we can try, what we can do with this syndrome, we can try to locally reduce it just by adding boundaries. And since it's a local update, yes, each time we reduce the weights, each time we just add some constant number of, so in terms of the distance, yes, when we try to reduce, so what we do, we just update. Yes, we just consider x plus delta x, which this delta x corresponds to this local boundary that we add. But this delta x is constant size. And since each time we reduce the syndrome, yes, we can reduce it to 0, for example. If we can reduce it to 0, then and in fact, we can reduce it to 0. Why we can reduce it to 0? Because if we cannot, yes, so here I consider that the weight of the syndrome is smaller than this locally minimum distance. And if we start with the syndrome, which weight is smaller, this locally minimum distance, then this chain cannot be, so it should be reduced to 0, because Otherwise, we would have locally minimum chain, locally minimum code words, yes, with smaller weight than this. And it means that if we start with the syndromes, which is small enough, yes, which is smaller than this value, then we can reduce it. And we can reduce it to 0, and we can do it in, so the number of steps that when we update this X is proportional to the original weight of this syndrome. And these deltas that we add, it's also proportional to the weight. And this is exactly how we get that HX is approximately the same as HX, yes? This is a property that we need to show for locally testable codes. And this works for sufficiently small X, but it is easy exercise to show that it's not a problem for this definition, yes, because we can still adjust this constant soundness parameter, so everything works here. So we need for local testability, we just need to make sure that this happens for sufficiently small syndromes. And this is a key ideas behind at least our proof. And what is interesting that is what I described to you also give you a decoder. This is a decoder for the quantum code. If we consider, or for locally testable code, yes, so it also can be considered as a decoder because we have some syndrome and we locally try to to reduce its weight, and we go to the code word. So it's also a local decoder, and it is much easier than the one that you were shown in these lectures, yes, by Sipser and Spielman, because so the proof that this thing is high is really hard, but the decoder is much simpler. Sorry? Yes, it's sequential, yes. And why I mentioned this decoder, but because this decoder also works in the context of QLTC codes. In the QLTC codes, we have 5 layers, and if we yes, and if we apply it here, so we can also decode in the linear time using this idea, but we apply it for these layers because they have LTC property, and we use exactly the same decoder, and it will give you a very simple decoder for quantum LDPC codes. Because for quantum LDPC codes that we have right now, we have quite sophisticated decoders, but this decoder is much, much easier. So potentially, so why we're also interested in QLTCs, they will give us very, very simple decoders. Okay, I think I'm done. Do you have any questions?
Yes.
That's an interesting question. I think, yes, maybe for good codes, possibly yes, but we don't, right now we do not have any formal way how to show it. This is true for all the constructions that we know, but we do not know any formal way to reduce one. Yeah, so what I was trying to show that this quantity is indeed works for both. So if this quantity is high enough that it gives you both, yes, but we do not know whether we can go just for one to another. So maybe we need some additional quantity, maybe. Small set compoundary expansion immediately implies good distance, but I'm not sure. Maybe Max can comment on this. I'm not sure whether it implies. It implies. Okay. Okay. Yeah, you can use different properties, but as I said, so there is no direct connection. So just from the distance of the code to the, and as far as I know, there are no such way how to prove it. Yes, but maybe yes, maybe we have some. There is some connection between them. Yeah. Oh yeah, this is the decoder that I was trying to describe here. So we just add these stabilizers, if you know what I'm saying, local, and try to reduce the weight. And we apply it on this layer. I mean, so we apply this idea for this part. So we can see that it's like LTC, and so we can try to reduce the weight of this. So this is the LTC, and we can run linear time decoder for this. And this is also LTC. And here we can run and reduce the error. Yes, so we can run these decoders on these parts, this part and this part. And this is the same decoder, yes, as for example, you can use any decoder, linear time decoder, for example, the one that was proposed in the paper by Dinur. Yes, they also have some similar decoder. And you can run it because these LTCs, they naturally comes with, at least the ones that I described, they naturally comes with the local decoder. If we prove these LTCs in this way, they naturally comes also with the decoder. So you do not need to construct decoder separately. So it comes from just from this high value